Radio astronomy is the study of the universe through radio waves. These radio waves reach us from many celestial objects such as stars, galaxies, and planets. Radio waves generally arise from the highly energetic electrons and magnetic fields often created in the aftermath of violent events occurring in the universe. Celestial objects radiate in different regions of the electromagnetic spectrum, such as X-rays, ultraviolet, visible light, infrared, and radio waves, depending upon the physical conditions present in them. To study different types of radiations in the electromagnetic spectrum, different types of telescopes are used. To study radio waves, radio telescopes are used. The radio telescope, a basic tool of radio astronomy, consists of a reflector, a feed, and a receiver system. The Jodrell Bank radio telescope in England is an excellent illustration. In India, the first radio telescope was installed on the picturesque slopes of the Nilgiri Hills in Ooty. The installation of this powerful telescope was done by the Radio Astronomy Center of the Tata Institute of Fundamental Research in 1970. Basically, the OOTY radio telescope consists of a reflector, a dipole feed, and a receiver. The radio waves first fall on the reflector, which focuses them on the dipole feed, which in turn collects them. These weak signals are amplified and processed by a sophisticated receiver system. The OOTY radio telescope has been designed and fabricated indigenously. What makes it unique is its design. The OOTY radio telescope has a parabolic cylindrical reflecting surface. This surface is 530 meters long, 30 meters wide, and is placed on a hill whose slope is about 11 degrees in the north-south direction. But why has the telescope been placed on a hill slope? Mr. Joshi of the Radio Astronomy Center explains this with a model.
Here is a model of the OOTY radio telescope. It is half a kilometer long in the north-south direction and 30 meter wide in the east-west direction. I have made this model bigger compared to the size of the globe for the sake of clarity. Suppose we want to put this telescope right on the equator, say in Africa. Then I have to place it horizontally on the surface of the Earth so that its axis of rotation is parallel to the axis of rotation of the Earth. Now let us put it on the North Pole. Here I have to place it vertically up like this so that its axis of rotation is again parallel to that of the Earth. The Earth rotates from west to east. So to follow a source in the sky continuously, I have to rotate the telescope from east to west with the same angular speed. Now let us place this telescope in OOTY. Here I have to put it on a slope whose angle is 11 degrees, which is equal to that of the latitude of OOTY, and then the axis of rotation of the telescope will be parallel to the axis of rotation of the Earth. We can track a radio source in the sky with the OOTY radio telescope for 9.5 hours continuously.
The tracking is done by pointing the telescope in the north-south direction. This pointing is achieved by electronically phasing the array of 1,056 dipoles placed along the 530-meter long focal line. The reflecting surface of the OOTY radio telescope is made up of 1,100 thin stainless steel wires, each being 530 meters long and 0.38 millimeters in diameter. These wires are supported by 24 parabolic frames placed in a row. The distance between two such parabolic frames is 23 meters. The OOTY radio telescope operates in the band of 322 to 328.6 megahertz. Its effective collecting area is about 8,000 square meters. The large size of the telescope makes it highly sensitive, capable of detecting signals from a mere 1-watt radio station located 10 million kilometers away in space. The radio waves collected by the radio telescope are taken to the sophisticated receiver system through underground cables. These signals are then amplified and taken to the chart recorder. The same information can be stored in the computers also for further processing of data. Unlike an optical telescope, one cannot see directly through a radio telescope. The radio waves received by radio telescopes are processed by computers, and the final image of an object is produced on a television screen. The main objective of the OOTY radio telescope was to study the origin and evolution of the universe. This could be done by means of the angular diameter flux density relationship of radio galaxies and quasars. In a study like radio astronomy, accuracy is very important for correct results. So to study the origin and evolution of the universe, a resolution of better than arcsecond is required. This was acquired by a technique called lunar occultation. There is a radio source in space and the radio telescope on the Earth. Whenever the moon, during its movements in the sky, comes between this radio source and the radio telescope, the phenomenon of lunar occultation takes place. By observing the gradual disappearance and reappearance of a radio source, it is possible to determine its angular diameter with a very high angular resolution of better than an arcsecond.
Thus, the lunar occultation technique enables us to achieve high angular resolutions with moderate-sized radio telescopes. Using this technique and the OOTY radio telescope, we have obtained angular diameter data and precise positions for more than 1,000 radio galaxies and quasars. The angular diameter flux density relation shows that on an average, in the earlier epoch of the universe, the linear sizes of the radio sources were much smaller, thus supporting the Big Bang cosmology.
The facilities at the Radio Astronomy Center OOTY have been further expanded. 8 small-size 23-meter into 9-meter telescopes have been installed. These are spread up to a distance of about 4 kilometers around the OOTY radio telescope. This as a whole is known as the OOTY synthesis radio telescope. This radio telescope makes possible detailed radio maps as if taken down by a large single radio telescope of 4 kilometers diameter. Signals from these telescopes and the OOTY radio telescope are combined with each other using synthesis techniques. The data are analyzed using a sophisticated image processing system. Several interesting results have been obtained using the OOTY synthesis radio telescope in the subjects of supernovae remnants and clusters of galaxies. Radio astronomy has moved the boundaries to the edge of the universe and revealed spectacular and enigmatic objects and phenomena. There must be many more exotic and fascinating objects in the heavens. awaiting discovery. It is for us to discover them with the help of radio astronomy.
Man has been fascinated by the heavens always. The study of the celestial bodies is the subject of astronomy. Right from the good old days, the skies were observed by man. The constellations were observed by means of naked eyes. And afterwards, as technology advanced, telescopes were built, and optical telescopes have been used for astronomical research. This has been done by photographing the celestial objects and taking spectra of these. By means of the photographs and the spectra, astronomical research had been carried on vigorously right from the days of Galileo on to the present time. Optical astronomy has given lots of information about not only our solar system and the objects in the Milky Way and all about the external galaxies. Optical astronomy has its own limitations, because the optical astronomer can work only during cloudless nights and moonless nights, and also only during nights. But at present, astronomy has expanded very much, and all the radiations, all the bands of the electromagnetic spectrum are used for exploring the universe. The first use of other radiation, that is radiations other than visible light, had been done since World War II. In 1932, Karl Jansky, a Bell Telephone Laboratory engineer, announced the discovery of radio waves from our own Milky Way galaxy. This was detected very accidentally. His project at the Bell Telephone Laboratories during the early 1930s was to find out the interference noises that were caused to the transoceanic radio telephone circuits. While he was doing this, he found static from the nearby thunderstorms, static from the distant thunderstorms, and also a hiss static. And this hiss static, like shh noise, he found that it was coming only from the sky, and after observations for nearly 1 year, he concluded that this hiss static was coming from our own Milky Way galaxy. And this is the beginning of radio astronomy, that is the study of the celestial objects by means of the radio waves that are naturally emitted by means of the celestial objects. By studying the radio waves, one can explore the universe. And after Carl Jansky, it was Grote Reber, an amateur radio enthusiast, who followed the experiments of Carl Jansky and tried to find out the distribution of the cosmic radio emission in the sky. He also found some subsidiary maxima which could be identified with certain objects like the radio source in the constellation Cygnus. Since then, there have been many telescopes that have been built all around the world. The first of its kind was at Jodrell Bank, England. And all these various radio telescopes around the world at various radio observatories have contributed to a remarkable discoveries of various celestial phenomena and exotic objects. Some of them are the radio galaxies, the quasars, the cosmic 3-degree Kelvin background radiation, and the pulsars. Also, many complex organic molecules have been discovered in the interstellar medium. These are really very remarkable discoveries. For example, the radio galaxies emit energies of the order of 10 to the power of 60 ergs, which means the equivalent of the destruction of a million suns. The energy that is generated by the destruction of or annihilation of a million suns is equal to 10 to the power of 60 ergs. These are very explosive phenomena. So there is a difference of the picture that the radio sky gives as contrasted to the optical sky. The optical sky looks very calm and peaceful, whereas the radio sky is very explosive, very catastrophic. So because it has been able to find out very exotic objects, this science of radio astronomy has been pursued very vigorously. For example, the quasars are supposed to be objects at the very edge of the universe, and because these objects are very compact and are supposed to be at the very edge of the universe, that is at a distance of about 10 to 15 billion light years, they emit enormous energies, even greater than 10 to the power of 60 ergs. But it is enigmatic that the energy source is not known very clearly. It is still a puzzle. Because radio astronomy is a science which is at the frontiers of knowledge, India also tried to build a radio telescope in this country. Encouraged by Professor Baba, Professor Swarup first came to India and then thought about this particular design of this radio telescope in the form of a parabolic cylinder mounted on a hill slope at this place. The hill slope is at 11 degrees 23 minutes, and this mounting this telescope along the mountain slope, hill slope, makes the axis of the telescope parallel to the Earth's axis at this place. And using this telescope, many interesting and significant scientific contributions have been made by the scientists of the Radio Astronomy Center.
astronomical observations made with the OOTY radio telescope have provided a support to the Big Bang model of the universe, according to which the universe was created about 20 billion years ago, and it was extremely small. Although this model is now accepted by theoreticians widely, it must be tested using all possible observational tests. Towards this objective, India is setting up a giant meter wave radio telescope, popularly known as GMRT. This radio telescope consists of 34 antennas, each about 45 meter diameter dish, parabolic dish. We have evolved some novel design for these dishes, in which we have utilized the fact that it does not snow in India, and also our experience from OOTY. Conventional antennas use lot of steel and a heavy design. In the new design, which we call SMART, S-M-A-R-T, the wire mesh is placed on curved rope trusses, which we jocularly call using Indian rope trick. Here is a design of this antenna. The main feature of this new design is that between the frames, these rope trusses provide a curvature on which this thin wire mesh is put, so that radio waves are reflected but wind passes through. This radio telescope is spread over an area of 25 kilometers. In other words, these 34 dishes are spread over 25 kilometer diameter, and using powerful modern computer techniques, it is possible for us to simulate a 25 kilometer diameter radio telescope.
As we have learned from Professor Govind Swarup, radio astronomy is a fast developing line of science. In India, the facilities for studying the universe and space through radio astronomy are expanding rapidly. The telescope at Narayangaon is fully designed and fabricated by Indian scientists in India. It will be the world's largest radio telescope when it is finished in 1992. Operating up to about 1000 megahertz, it will provide India with a powerful facility. It will also enable the students of radio astronomy to study further the subject right here in India, and will also facilitate all kinds of research on this subject. This progress in the field of radio astronomy has put India on the front line of the science scene.